All right, thanks. Hi, I'm Alex Greenebaum at Johns Hopkins and Space Telescope, and I mostly work on aperture masking, which is an interferometric technique. It's a complementary technique to chronography, and I've got a few examples of in the literature of how aperture masking has been used on previous telescopes. I work mostly on GPI and JWST. And how aperture masking has been used on previous instruments, VLT and Keck, to look for inside the regions, inside the gaps of transition disks, to look for possible planet formation regions and companions inside those disks. And in regions usually behind the coronagraphic spot. So that's why it's a complementary technique. So if you can hit the next slide. So aperture masking works by splitting up the pupil into a set of 10 holes, or into a set of holes. On GPI, it's 10 holes. So this is what the mask looks like on GPI, and it splits them up into unique whole pair vectors, so that no vector is repeated. And so this is really an interferometer, and so it can get interferometric resolution and contrast to get behind the coronagraphic spot. So it pushes a more aggressive inner working angle than a coronagraph, and at the expense of throughput. So it is a trade-off, but you can get into these regions and get closer and closer to your host star, and sort of complement the observations you make with a coronagraphic technique. So I'm working on GPI. This is what the perfect point spread function of the NRM on GPI looks like. And I have a poster number 18. So if you want, you can come find me to talk to me about data reduction methods I use for the GPI NRM mask. And some early results from commissioning our contrast levels, and how we'll follow up some of these studies on NIRIS, on JWST. Thanks.
Hi, my name is Jorge Lydia, and I'm going to talk about a bit about Kepler validation. So high-resolution images are crucial in the follow-up process of planet candidates detected by the transit method, like Kepler or Corot. So, and this is because as you can see, to get high accurate photometry, you need a large aperture and PSF. As you see in this high resolution image, the PSF of Kepler is drawn in green. You see, you include companions and contaminants inside the PSF. So you need these high resolution images. But either if you have an isolated KOI, you need to characterize, to quantify how sure you are that it is actually isolated. So you basically get this sensitivity curve here, and the next slide, please. So with this sensitivity curve, you can reduce the probability of having a blended undetected source. So the probability is basically this one in this first equation, but which is basically integrating this map. But if you have this high resolution image with this sensitivity curve, you basically remove everything above your sensitivity curve. So you can reduce the probability of having a blended undetected source. So you improve the candidacy of the planet. So, and we did that for 300 Kepler candidates, and we concluded that we improved this the candidacy of the candidates by more than 50% for more than 62% of our sample. Yeah, that's it.
Okay, my name is Rebecca Jensen Clem, and I'm going to tell you about the dark speckle method and how recent advances in superconducting detectors allow us for the first time to take full advantage of this method to achieve very high contrast. So the dark speckle method states that for very short exposures, you will see highly destructive interference in the speckle pattern. And a planet, however, will stand out because as you take many short exposures and you build up this dark map of your frame, the planet will always contribute some intensity, so you will never see such dark nulls at the location of the planet. Next slide, please. So in this frame here, you see 10,000 such short images, and this frame is showing you how many instances of zero photon counts resulting from these areas of highly destructive interference have arrived. And so because this is the reciprocal of how many zero photon events you saw, the planet stands out as a very bright object. However, in order to take full advantage of this method, you need to have a photon counting detector with zero read noise and zero dark current. It also needs to take exposures fast enough to freeze the atmosphere and observe in a wavelength band that has very low background counts, such as the visible. So for the first time, we are building such an instrument that will take full advantage of the dark speckle method. And that will use a new superconducting detector technology called MKIDS. And we'll be using this with the Palomar P3K adaptive optics system, which can push into the near infrared and into the visible. And we will use this detector behind the P1640 and the upcoming Vector Vortex SDC coronagraph. And Seth Maker will now tell you more details about this instrument. Thank you.
Okay, so I'm Seth Maker from UC Santa Barbara. So Becky just described the dark speckle technique, and this is Darkness, the camera that we're building for the Palomar telescope to take advantage of this very promising technique. So as she said, the thing that makes Darkness unique is its use of microwave kinetic inductance detectors. I don't have time to get into the operating principle, but these are superconducting detectors, so suffice to say it's very different from typical optical detectors. But the thing that's remarkable about it is that it gets you individual photon counting with zero read noise or dark current and intrinsic energy resolution. So you get low resolution spectroscopy with no dispersive element. Darkness will be optimized for a 0.7, 1.4 micron bandpass, so we're hoping to push into visible wavelengths more. And this is just the CAD design of the doer, designed to fit into the Faro envelope, and so we can mount easily with Palm 3K, 1640, and SDC. Can we go to the next slide? So these are a couple of simulations of the performance. As I said, because we have energy resolution, we can apply spectral differential imaging, and this is a not very interesting graphic of dark speckle technique. And so you can see here in INJ band simulations, the black curve is raw contrast from 1640, which is a pretty well understood instrument at this point, and these match fairly well with spectral differential imaging applied just as an order of magnitude based on their current results. And if you believe the analytical expressions for dark speckle technique, you can see a drastic contrast improvement, more than an order of magnitude in J-band, and actually, if you also believe the current atmospheric models for the HR8799 planets, we should be able to pull that out in I-band. So if you're interested in this, come look at our poster, and I can tell you what the acronym stands for.
Okay. Hi, my name is Thomas Lozito. I'm a UCLA grad student in my final year working with Mike Fitzgerald. And I'll present to you a new, faster method that my co-authors and I have developed to forward model and correct for ADI self-subtraction of extended emission. This correction is crucial for analysis of objects like circumstellar disks because angular differential imaging and the related Loki algorithm suppress speckle noise, but they also self-subtract disk surface brightness, biasing your photometric and morphological inferences from our data. Here's how we forward model this self-subtraction. Take an example ADI data set in which the disk modeled here is a dust ring is at a different position in each image. And then patterning our forward modeling scheme on Loki, we select an image as our target image, grayed out here, and exclude reference images close to it in time, and then make a weighted linear combination of all remaining reference images. We repeat this for each target image in our data set, and then we average together all of the linear combinations. Now the weighting coefficients change with radius, so we repeat this process for all radii until we've constructed a complete self-subtraction function that precisely describes the self-subtraction at each location in our Loki processed image. Now all of this boils down to a few simple equations, but you don't have to worry about the math because you can read all of the details in our recent AppJ paper. And the main advantage of this algorithm is its speed, which results from expressing the self-subtraction function at each radius as a convolution. So this does not require a Loki reduction of each model, meaning we can compare hundreds of self-subtracted models to our data in the time it takes existing algorithms to compare just a few. Here's an example of the self-subtractive model our algorithm makes for an input model, followed by some similar examples for different sets of Loci parameters. ADI processing introduces some degeneracies, which you can break by comparing your data with multiple Loci parameter sets. And if you have any questions, please talk to me. Thank you.
Good afternoon, I'm Marie Gouff, I'm a postdoc at STSCI, and I will talk about a new method of image post-processing for direct imaging that I developed during my PhD in collaboration with Onera and IPAG. It was in the context of the sphere instrument, which provides some multispectral images, and what is fun with multispectral images is that we can use the multispectral redundancy to disentangle the signal of the object we want to detect from the speckles. And the base of the method is the spectral deconvolution by Sparks and Ford. And what is new here is that we have an imaging model of instrument which link the instrumental aberrations to the speckle in the image. This method has several advantages. It is an evolutive method, and also because we can estimate the instrumental aberration, also it paves the way for calibration by post-processing. Here we can see some very promising results that I got on simulated images. I show that it is possible to estimate the instrumental aberration and the object we want to detect jointly, and also that by increasing the number of wavelengths we use for the estimation, here we have two wavelengths, here 6, the detection is improved. The story continues. I will continue to develop this method in the context of space-based instrument object, in the context of AFTA, and also there are Faustin Cantaloupe, who will continue to work on the ground-based instruments. So if you have some questions in my poster, thank you.
Hi, I'm Statia Cook. I'm a postdoc at the Museum of Natural History, where I'm a member of the Project 1640 team, but I also work on observations and analysis of solar system giant planet atmospheres, which is what I would like to introduce quickly today. Here's an example of the data we are looking at. This is a Keck OSIRIS image of Neptune, and for each pixel in this image, we have a spectrum like the one shown here in blue. To analyze the data, we have a retrieval model, which consists of 2 components. We have a forward model, which is a Python-based radiative transfer code, which solves the radiative transfer equation given some model of the atmosphere to produce a synthetic spectrum like the one shown here in red. And the second component is a retrieval method, which gives you an estimate of the parameters in your model using the forward model and your data. Go to the next slide. So here is a figure that shows some results of one of our fits. This is a fit to the data shown on the previous slide. And what we see here is the 1 and 2D projections of the posterior probability distribution. This gives us an estimate both of the best fit parameter and also the uncertainties in the parameters. And for this example, I'm showing mostly parameters that have to do with the a haze that we've put in our model, so things like the thickness of the haze and the location of the haze. But we also fit things like temperature and abundances of different molecules. So the ability of this model to explore a very broad parameter space is one of its advantages. So we're not restricted to particular descriptions of the cloud. Holy cow. Anyway, we're extending this model to be applicable to other targets. And if you have any questions or would like to discuss this, please either talk to me later or give me an email. Thanks.
Okay, all radio velocity instruments ever built have been seeing limited. We are building the world's first diffraction-limited Doppler spectrometer. Okay, when you turn on the AO system, you reduce the input image by a factor of 30, and that translates directly to spectral resolution. So you get R of 110,000 in the infrared using off-the-shelf parts. You reduce OH emission by a factor of 30 squared, and you can use single-mode optical fibers to completely eliminate modal noise. Okay, when your instrument also shrinks by a commensurate factor. So instead of being the size of a car, it is the size of a mailbox, or maybe a rich person's mailbox. It's about this big. And you can use more exotic materials, such as Invar, which allows you to achieve 10 times less. It has a 10 times lower thermal expansion compared to aluminum. Thank you.
Hey, good afternoon, everyone. My name is Eric Bechter, and I'm one of Justin's graduate students, and I'm part of the iLocator software development team at the University of Notre Dame. Next slide. Okay, shown here is a photon noise limit calculation for our new instrument iLocator compared with HARPS. Plotted are 0.9 meter per second contour lines for each instrument as a function of apparent visual magnitude and spectral type. And so above each contour line for each instrument is the available space to basically detect new exoplanets. And because iLocator can utilize the full collecting area of both 8-meter dishes at the LBT and is capable of working at the diffraction limit, we can target significantly dimmer and cooler stars, enabling us to search for previously undiscovered exoplanets in new systems. Thank you.
Hello, my name is Chris Matthews. I'm a graduate student working with Justin Krepp at Notre Dame, and I'm just presenting some more details on our characterization of the white dwarf HD 114174b. This image here is the LBT L-band discovery we made. We originally attempted to recover it in the L-band with KEK-AO and NERC-2, but even with aggressive PSF subtraction, we couldn't recover it. And the addition of the new L-band photometry point allowed us to better constrain the models for the evolution of the white dwarf, and revealed an apparent discrepancy between the age of the cooling age of the white dwarf and the age of the primary star determined by gyrochronology and isochronology. So this is an outstanding problem, and we're hoping to get some more data to help characterize it better. Thank you.
Good afternoon. My name is Andrew Bechter. I am yet another one of Justin's grad students working on iLocator. I'd just like to quickly present an auxiliary science case that we have involving binary systems. Next slide. Plotted here are binary systems with at least one confirmed planet. As you can see, most of the detections occur in binary systems with at least 100 AU projected separation. That's because all radio velocity instruments that currently exist are seeing limited. Now, as a diffraction-limited spectrometer, iLocator will be able to resolve light in binary systems with much closer separation than ever before, unlocking this completely new parameter space to find planets in new dynamic binary systems. Thank you.
Hi, I'm Elodie Choquet. I'm postdoc at STSCI, and I will present you the two projects I've been working on in 3 slides, but 2 minutes. So the first project is design and development of the HiCat testbed, which purpose is to study wavefront sensing and control strategies for high contrast imaging instrument for the next generation of complex aperture telescopes, such as AFTA mission or the Atlas telescope. Here you can see a picture of the test bed with its dozen of optics aligned down to 12 nanometers RMS wavefront errors. Next slide. So the testbed is for the moment equipped with a classical Leo coronagraph, and you can see here the first coronography PSF that we get with this testbed. The next step is to implement one of the two Boston deformable mirrors that we plan to use for wavefront control studies, and then to implement a segmented mirror from Iris.io to simulate the segmented primary mirror of the telescope. Next slide. And the second project I've been working on is Alice project, which consists in consistently reprocessing the entire HSC NICMOS coronographic archive with advanced post-processing algorithm, such as a CLIP algorithm. The archive is equipped, is composed of about 400 stars, and so far we have discovered a dozen of companion candidates and 6 debris disks never seen before in scattered light. Which increases their number by 30%. And we are following up all these targets, both with ground-based telescopes and HST with a WIFTX3 instrument for the point sources, and with a STIS coronagraphy for the disks. And thank you.
Hi everyone, so my name is Faustine and I'm working on image processing methods to detect and characterize exoplanets. So I'm actually working on 2 methods and they are both based on inverse problem solving. So the first one is called Andromeda, and it relies on, it first performs an ADI, so angular differential imaging, in an optimized way specific to the algorithm. And from the resulting pseudo images we obtain, we establish a model, and along a model of noise consistent with the pseudo images, we can analytically resolve the maximum likelihood. So it's based on the maximum likelihood. Sorry. So we have 2 unknowns: the position and the flux of the planet. So it provides 2 maps. When solving the maximum likelihood. So the first one is a probability map, enabling to detect companions and derive their accurate position. And the second is a flux map, on which we can read directly the flux of the planets. So the main interest of this method is first, the first map, you can threshold it by a constant value and perform an automatic detection, which is brand new. And you can also have the subpixel position of your companion, which is quite interesting. And the other thing is, contrary to Loki or PCR, widely used methods today, you can directly extract the flux from the flux map. It's pretty good. So the second method I'm working on is aims at processing multispectral data from IFS, for instance, in integral fit spectrograph. So Marie has already talked about that, so I won't go back on it, but my goal is to prepare this algorithm she built for real data. For instance, I have to build a refined model more realistic than what exists now, and also to introduce any information about the instruments or any prior knowledge about the planets, and do some work. That's it.
Hello, my name is Erin White. Unfortunately, this talk and the next talk are conceptually out of order, so buffer this all in cache until I'm done. I work on the stability of the extraction of spectra using Project 1640 and one of our pipelines called the S4 pipeline. So at this point in the pipeline, we already know where a companion is, and we want to extract the actual spectra from it. So S4 uses a principal component analysis model, and what this does is S4 spectra then models the speckles in both wavelength and in time, and then it uses this knowledge to determine how much of the flux should be associated with the speckles and how much should be associated with the companion. As one might expect with a model like this, it's actually fairly complicated, and there are plenty of knobs that we can turn on the input parameters for this, and we don't know a priori which input parameters we should be using for this model. They're entirely dependent upon the conditions under which the data was taken. So we have 2 methods that we use to determine the optimal parameters for this model. One is a fake insertion method, where we take a known spectra and we insert it into the data in an annulus around the star at the same radius that the companion is away from the the star. And then we use S4 to just extract this inserted spectra, and then we compare the inserted spectra with the extracted spectra, and we can do this over a range of parameters and determine which ones are the proper ones to use. So that gives us an ensemble of input parameters that are optimal. The other method that we use is we look at just the companion, we give it a large ensemble of input parameters, and then we look for ranges where the extracted spectra is actually stable as we tweak our input parameters, and that gives us another ensemble of input parameters that are optimal. These overlap, they give the same spectra, and they agree with the other method.
Okay, I'm Ricky Nilsson from the American Museum of Natural History, and I will just give you a brief overview of one of the data reduction pipelines used for high contrast imaging and planet detection with Project 1640. So what we have on the uppermost left image is the raw image on the detector, which consists of these tiny, tightly packed spectra, and these can be automatically located and extracted by the PCXP module, which gives us a data cube, basically 32 stacked images in the JNH band. And then we have these astrometric grid spots, which tell us where the star is located behind the mask in each image. And we use the CAX module to track the grid spots and calculate the atmospheric and instrument dispersion. And then the dispersion corrected cubes are sent to S4 detect, which models the noise speckles both through wavelength and time using principal component analysis. Next slide. And S4 detect spits out, well, among other things, residual cubes, which can be cross-correlated with companion model PSF to give us these so-called detection maps. And sometimes, like in this case, you can clearly see the companion in the detection map. At other times, we need to use Planet Finder, which calculates a local signal-to-noise map and also automatically detects significant peaks in the map. And then we send the coordinates of this to S4 Spectrum, which Erin just told us about.
Thanks. Hi, everyone. I'm Jonathan Aguilar, and I'm the third person in a row telling you about Project 1640. They told you about the S4 pipeline. We have a separate data reduction pipeline called CLIP, which Elodie also mentioned we use on the ALICE pipeline from HST data. So what CLIP does is it takes a library of reference PSFs, and it breaks each image up into regions, and it models each region using PCA in a particular basis called a Karhunen-Loeve basis. Apologies for my pronunciation. And what's interesting about this basis is that if you have a limited number of modes, it actually gives you the optimal information given that limited number of modes. And so what you can do when you have data coming off of an IFU, like we have at Project 1640, is you can actually use the data cubes for your reference PSFs. What you want out of the reference images, of course, is you want only the PSF and no signal from the companion. And so the way you do this is the speckles, which are the PSF that you're modeling, scale as 1 over the wavelength, but the companion doesn't. As we saw nicely in the talk before, it's off-axis, so it goes right through. And so what you do is you just simply move a couple wavelengths over so that the companion is no longer in the zone. I guess, let me rephrase that. You rescale all the slices so that the speckles are on top of each other, and therefore in this rescaled version, the planet is moving, the speckles aren't moving, so the planet moves out of your zone, and then you have your reference PSFs with no signal. And it's really nice. So what we have here is a scaled image and then a reduced image. In the scaled, you have all these speckles. In the reduced image, the speckles are gone. You see some noise from the detector, that's the stripes, and then the companion is circled up in the upper left-hand corner. Now we have a number of modes, and that's all my time. All right. So.